Man dachte, es ist eine gute Idee, man stellt jemanden kurz dahin, der den Speaker begrüßt, auch weil das Ganze aufgezeichnet wird. Ich bin Markus von der Java User Group Switzerland und ich darf auch noch Werbung machen, die mache ich auch noch ganz hier ungeniert. Wer bei uns einen Vortrag macht, der bekommt sowas Tolles hier, so ein echtes Schweizer Messer, so ein Unikat mit ganz tollem Aufdruck. Bitte meldet euch bei info@jack.ch. So. Das geht hier heute um einen Vortrag vom Per, der hier extra angereist ist. Ich glaube aus Palo Alto, dort ungefähr lebt er wird es gleich erzählen. Und er wird etwas über 5 Features erzählen von Java, die die meisten noch nicht kennen.
Ja.
Und dann übergebe ich schon an dich und wünsche dir viel Spaß.
Vielen Dank. Ich werde in Englisch sprechen. Ja. So welcome everybody to this presentation. Oh, this is really a cool scene. Where's the skateboard? Okay, yeah, I like that. So the title here is 5 Java features you didn't know about, and the subtitle is number 4 will shock you. Okay, I'm Per. I've done a lot of talks around the globe, maybe 50 right now. I'm a co-writer of Modern Java, written Oracle Java magazine. I have my own blog and so forth. I also run a company called Speedment. I live in Gothenburg in Sweden and also in Silicon Valley. I lived there for 3 years, just came back. So just before we start, this presentation contains learnings from the open source Speedment, which is free. You can download it, you can take all the source code there and do whatever you want with it. So this is, okay, it's some kind of promotion, but you can all use it for free. There's one item about an enterprise, but there's also a free version that you can download. You don't have to pay anything to try out this technology. And some features are easily used, and some features are more advanced. So you might use 2 or 3 features tomorrow, but some are more kind of advanced. So let's go back, way back to Java 1.0, and this is a kind of a class I used to work with at that time. This was around the epoch 800 million, so it was a very long time ago. So what is this really? Well, it's a podio of some sort. We have getters and setters, and we have like 3 properties, 2 strings and an int, but we have no clue what it is. If we reveal the comments, we get some clue what it is. It's obviously a person, and we have first name, last name, and social security. But why would we ever use a bean like this? The answer is, it was faster. If you shorten your identifiers in the beginning of Java, you get maybe a 30-35% increase of speed. That's really amazing. Why? Because we didn't have the JIT compilers. So everything was interpreted all the time. And of course, we have to sacrifice things for this. Obviously, clarity. But what about when we got an exception? What would you make out of this? And what about reflection? I won't even go there. Really terrible. So let's talk about the first feature, objects on the stack. So we have usually when we allocate a Java object, we allocate it on the heap. So there's a life cycle for a Java object. We have to allocate it first, then we use it, and then we dispose of it. And actually, the disposing is the most advanced thing for the JVM. We have to make sure that our object is not referenced from another object before we can discard it and throw it away. So why not allocate a short-lived object on the stack instead? The stack is much smaller, and you just push it, and when you're done, you just pop it. That would be much better, wouldn't it? So let's take a poll. How many of you have actually allocated Java objects on the stack? 1 person. 2 persons. Great. I'm going to ask this question after this and see if there are more. So let's go to the problem. We have here an immutable point class with x and y. We have a constructor, and we have getters, and there is a toString method here. So let's zoom in onto the toString method. This, I know, this is no longer the preferred way of writing a toString method, but anyhow, it's a good illustration of the concept. So we create a string builder first. We kind of do stuff with it, and then we convert it to a string. That's good. And if we go about and create a point like this, and then we invoke this toString method 1,000,000 times, what will happen? Will we create 1,000,000 string builders and 1,000,000 strings? That is the question. And the answer is, it depends. It depends whether we can observe those objects or not. So this sounds like kind of quantum theory. If we observe them, they exist, but if we don't observe them, they don't exist. It's really weird. So let's dig into the details. Let's create a program that kind of gets rid of everything that's there when we start. We invoke our sum method, and then we wait for an enter key so that we, from the side, can see what's on the stack. And then we do the same thing again, do exactly the same procedure. What will happen? Well, let's see. So if we start JMap on the side, and we get this for the first run. We have created about 50,000 strings and about 30,000 string builders. Not 1 million, that's weird. And it's getting even mysterious. To the next invocation of JMap, we haven't created a single string builder. And we will have a small bunch of strings, presumably only the strings that were there from the beginning in the JVM when we first started it. So what's going on? Well, it's something called escape analysis. And this is something that the JIT compiler does. More specifically, it's the C2 compiler in the JIT compiler that does this. And it kind of sees if a variable can escape that method. So in this case, you can see that the string builder cannot be viewed outside the toString method. It's local. And it cannot be viewed by another thread, other than the invoking thread, of course. So if you kind of have this analogy with the Russian Matryoshka dolls, this smallest doll can fit into the second smallest doll. So it's kind of hidden. So that's cool. That means that we can actually allocate the object on the stack. And it's shown here as an SB prime because it's not really an object. I will come back to that later on. So this can, of course, be combined with inlining. Now, inlining is an optimization feature that the JVM does. It flattens out a lot of invocations of methods so we can look at the bigger scope. And we can see now that in the map function there, the string that's produced by the toString cannot escape the map context. So now, 2 dolls can be fit into the third smallest doll. That's good, because now we can allocate both the string and the string builder on the stack. Wow, we're getting somewhere. And if we look at the entire program, we see that the point is actually immutable and cannot be changed. And the in-stream range is from 0 to 1 million. That doesn't change. And the map will always result in something that's 10, because the point will never change, and it will always return a string of length 10. So in theory, we can put everything in a gigantic doll and see that this is 10 million. So we don't have to invoke anything. But that might be in some distant future in Java evolution. That's not happening today. But in theory, it can do. So what happened? Well, after 10,000 calls, the JVM compiled the toString method, and the old code path was replaced by this new compiled code path. And after 50,000 calls about that, the compiled code was activated. So it's like we're running on this left-hand track here, and we run on this old commute train, and suddenly we get promoted to an express train on the right-hand side and just dashing away. So this explains why it was 50,000 objects and not 1 million objects in the first run. It also explains why it was 0 objects in the second run. So this is not quantum mechanics, and that's good news, because who understands that? No one. So it creates a representation of an object on stack rather than on a heap. And the stack objects, they are kind of allocated instantly without memory allocation because it's inherent on the stack. And they are also cleaned up inherently. When we go out of scope, the stack pointer is restored. So it's virtually freed for nothing. And it can be much simpler than the heap counterprods. It doesn't have to have all the bells and whistles of a normal object. It doesn't have to have a class pointer. It doesn't have to have synchronization methods or support. And actually, synchronization can be removed because we remember that escape analysis tells us if the object can be escaped and cannot be observed by another thread. And because it cannot be observed by another thread, we can just remove synchronization methods. It's like if I have a string buffer here instead of string builder, it will run equally quick because we can just remove synchronization because there are no other threads involved. So in this way, an object can appear as something else that runs much faster. Okay, the good thing with stacks is that the probability is always 100% that the stack is in the CPU cache, so it's always very fast. And it's the C2, as I mentioned, the C2 compiler performs escape analysis, so you may make sure to run in server mode if you want to take benefit from this. Usually the C2 kicks in after 10,000 invocation, but you can set that. This is a big kind of question mark when it kicks in, and it's out of the scope of this presentation, but usually it's 10,000 invocation. Escape analysis can span over several call levels, and overriding finalize prevents stack allocation. I know we are told to stay away from overriding finalize, but this is yet another reason why you should not do that. Why is this? Why can't we do stack allocation of objects that override finalize? Someone? Because finalization is run by another thread, so it can be observed by another thread, and thus it cannot be allocated on the stack. So there's a heavy price for this. Okay, in theory it also allows a scalar CPU representation of objects like longs or ints. If it does, I don't know, but that might be a future thing to do. Okay, so this explains, for example, why returning optional can be very cheap. You might think that we create an optional each time we return it, but in theory, but in all practical sense, we don't do that. It's just on the stack. And this also enables stream to be performed because all the internal mapping operations, they are kind of for free, or not almost for free, because you don't have to create those intermediate objects. And there is a version of the VM called Grail VM, which comes with a new C2 compiler, which is much faster. It's able to flatten out the code much better. So we can gain massive performance, for example, with streams. Have you guys tried the Grail VM, some of you? A few guys. It's very interesting. You will get, in some sense, an enormous performance increase. It promotes local abstraction, so we don't have to sacrifice code clarity for performance. No compromise. Good. So I will ask you this question. Have you ever run Java and invoked the stem method more than 10,000 times? Well, then you have allocated objects on the stack. Good. Check. Next item, proper performance testing. So there's something called micro benchmarks, which is kind of the analogy to JUnit tests. You can fail early, you can assert that the code is performant, and you can reproduce problems. It's also good for exploration. I mean, it's very hard to tell if one method is faster than the other because of those things that happen under the hood, for example, stack allocation or inlining or stuff like that. So it's very important to understand before you optimize, is it really worth this? So let's start with a very easy example. This is a pattern I have used, and I guess most of you have used. How many have used this pattern? Everybody. What's the problem with this? Well, I can tell you something. Actually, this measurement can result in a negative value being returned. This compute can complete in negative time. And that's not either quantum mechanics. It's because that the current time millisecond can be adjusted by a time protocols over the internet, for example. So this is not very reliable. So let's improve. Let's use nanotime instead. This is a monotonic, and it also has better resolution. But it's still not a good idea because we don't know if our process gets swapped out, for example, in Linux or what's going on. There's also another problem. You have to make sure that your benchmark completes in 292 years. Otherwise, it will wrap around. So keep that in mind. Okay, so what does JMH do? It provides you with a lot of things. Like you can have black holes that really ensures that you are going to consume the results you're producing so that they're not optimized away. You can run several batches, so you can kind of filter away statistical noise. You can see the real C2 performance because there is a warm-up period so that all your method has been optimized. And it avoids kind of dead code elimination and stuff like that. That can kind of ruin your experiment. So this is just an example how difficult it is to really ensure that the CPU does something. This guarantees that this method will not be optimized away. We have some kind of variable with it set to some random value, and then we fiddle around with it, and then we very rarely update the consumed CPU, because if we hadn't updated the CPU, the compiler might just have optimized away the code. So you can see that the likelihood that the long is 42 is almost 0, but that's not really 0. So therefore, this code can't be optimized away. So this just shows how difficult it is to do a real test. So let's have 3 tests. We test the performance of different adders. So we use an atomic long, we use a long adder, or we can use our own object, which is a mutable accumulator that I will show on the next slide. And each of them have an int stream, return maybe 1,000 or 1,000,000 values, and we can test the performance. And note the benchmark note. Instead of test, we annotate them with benchmark. So this is the very simple accumulator. It's a mutable accumulator, so it has a sum, and it has an add, and merge, and a get method. Very simple. So we also test the parallel performance, because obviously in some cases we would like to have good parallel performance. It's the same, we just add the word parallel for each stream. And then we start a benchmark test. It will do a lot of warm-up, it will do measurement iterations, and we will get some results. So this shows the progress of each and every benchmark we do. And then we get a summary. And we can take this summary here and paste it in some tool that presents graphs like this. So here we see the custom accumulator on the left-hand side that we wrote is the best, at least for parallel execution. And the other is good, but look at the atomic long. When we go parallel, it's really a disaster, and that's a mini shocker. Why is the atomic long so slow when we run it in parallel? Yeah, of course, because it has thread contention. So all those parallel threads, they will kind of wait in the center, so they get sole access to the counter and update it. So it becomes actually slower when it's parallel. Okay, micro benchmark wrap up. Do not clock, do benchmark instead. Outsmart the JVM, return the value or have it consumed somewhere in a safe way. And the learning from the test here is that the lock-free divide and conquer parallelism is good. That brings us to the third learnings. Short-circuit stream for massive performance gain. This is a little bit more advanced. So what if we are at point A and there is a complicated stream and we want to get to point B? And now the rhetoric question, wouldn't it be better to go directly from A to B than following this maze? Obviously, yes, but how can we do that? So let's look at the problem. We have a list of 3 elements, and we want to compute the size of that list. And of course, you can evoke the method size, the complexity of that is order 1, meaning that it doesn't matter if we have 3 objects or 3 million or 3 billion objects. It will take the same amount of time to return the size of the list. There is, however, another method we can do this, another way to do it. We can create a stream, and then we can count each element. And the problem, of course, it will be the same result, but the problem is that this is order n. It will actually produce a stream and count each individual object. So this is order n. So if we have 1 million objects, and then I have 2 million objects, it will take twice the amount of time. And that's not good, of course. So let's look at something called declarative constructs. For example, a SQL query is a declarative construct. We say what we want, but we don't say how it's supposed to be executed. So in this example, the database is free to solve this problem however it wants. It can, of course, iterate over each and every film, apply the predicate, rating it is PD13, and then count each and every of them. But it's more likely that the database will use an index. And it's likely that it will only use the index to see how many index fits this requirement, rather than going to each row and iterate over each row. The same is actually true for a stream. You might think that this says that you have to have a stream with all film elements. Then for each of those elements, you have to apply this filter. But that's not really the case. The first line says we should have a stream that represents every object. The second says that we shall have another stream that represents only those objects satisfying this requirement. Exactly the same as for the SQL query. And then we should count them. So a smart implementation of a stream wouldn't iterate over each and every film. It would use some other way of short-circuiting the operation. So This challenged our way of looking at streams. Are they glorified iterators, or are they really source-aware smart streams? For example, we can write our own list implementation that returns a stream that we have written ourselves, which is much smarter. So in this case, we just return, if we invoke the count, it will just return the list size. So this implementation of this stream is also order 1 for a list. Regardless of how big it is, it will take the same amount of time. And so we can move on. We can, for example, replace the skip. So instead of skip, we can update our source and view that list as a sublist instead of a list. And we can, by inductive proof, show that if we replace each and every intermediate operation, the entire chain can be order 1. So this is a kind of cool technology. Okay, is this legit? Can we really do this? Yes. From Java 9, it's even documented in Java docs. So, for example, in the case of count, elements can be optimized away, and they will never be seen with a peak operation. And this is perfectly legit. So, and that's now I'm talking about Speedment, which is an open source project that I manage. So the idea with Speedment is to really view the database as streams, as smart streams. So they kind of render SQL from Java streams. So you don't have to bother about SQL. You only work with type-safe lazy streams. So for example, this stream here, we have a stream where we filter out each and every film that is PG-13 rated. Maybe you don't know, but PG-13 is parental guide, 13 years. That's the system they use in the US. And we are only interested in films that are, have a length more than 1 hour. And then we want to sort it in film length. And as a second order, we compare the film title in reversed order. And then we skip the first 50, and we're just interested in the next 25 of those, and we just print them out. So the cool thing with this stream is that it will inspect its own pipeline and merge all those intermediate operations into a SQL query. So we will get this SQL query instead, which is typesafe. We don't have to care about SQL. We only use the language we love, Java. Cool. So, and you can try this. There is an initializer on speedment.com. You fill in what kind of Java version, what kind of database, and you get a project POM, and you can just start off and play around with it. Okay, source-aware streams, they can merge stream operators, intermediate and terminating, into its source. Java Stream is just an interface, so you can implement your own stream implementations. In principle, anyone can implement a source-aware stream, so if you want to have a homework, you can just write a utility method that takes a list and returns a stream which is smart. This is the way you can kind of play around with the concept. These streams are generally clever. They handle parallelism. They can inspect their own pipeline. They prevent reuse between different builder invocation of a stream. They manage close handlers, and they handle exceptions in the operators, and they release potential resources like database connectors or native memory, whatever they have behind the back. And some implementation even fans out to specialized int, long, and double streams, so you can keep your kind of stream smart, even though you map it to an int. And they can vastly increase performance, both sequential and parallel. Again, we can use clarity without sacrificing performance. So I think the stream is more clear than mixing Java and SQL together. Cool. Item number 4, holding terabytes of data in the JVM with no GC impact. I mean, we know that the garbage collector is slow, isn't it? I mean, sometimes the Java garbage collector can take minutes to execute, even slower than this man from some centuries ago. So the problem is really if we create, for example, a huge map with, let's say, 1 trillion of films, like we do here, and we store them in a map. We use the map film ID as a key, and we apply an identity function, so we just store the film in the map. So what's the problem with this? Well, we create a hell of a lot of objects. Many extra objects like integers and map entries are created. In fact, we can create up to 6 extra objects for each entry in the map. And each of those objects are subject to overhead and byte alignment, so they are kind of big. And many times we don't create a map with billions of objects and then just throw it away. It's likely that we will hold it for a longer period of time. And so the garbage collector has to evaluate all these objects over and over again. And it's also difficult to retrieve objects except for key value. What if we want to retrieve only objects that has a length over 60, like we did before? If we want to do that, we have to introduce a tree map for each and every field. And that's a tremendous overhead. What if we have 100 columns? Then it'd be 100 times more information. And this is not really doable. And most implementation of a garbage collector is not proportional to the number of objects we have. Rather, it's a quadratic dependency. It's like a cocktail party. If there are twice as many people, you have to shake hands with 4 times many people. That's bad. We don't like that as programmers. We just want to communicate with our computer. Okay, so this is how it looks like. And you're kind of running into the GC wall, we used to call it. So when you get over a certain threshold, you can't put in more. With the advent of new garbage collector, this boundary has been moved and been improved, but still there is a wall to run into. So the trick here is to move things from the heap and put them off heap. And that sounds very easy in theory, but how do you do that? Well, you have to do 2 things. First, you have to allocate memory, and then you have to communicate between the different memory domains. And basically, you can allocate memory in 2 different ways. You can use either the byte buffer, or you can use unsafe. And now it's getting more advanced, so bear with me here. So in the first line of code there, we allocate 1,000 bytes off heap. You can also allocate memory by mapping a file or allocating them on heap, but that's not so useful. At the bottom, you see how you allocate using unsafe. So in this case, we allocate memory 1,000 bytes, and we get the long, which is basically the address where this memory is located on our computer. So let's compare byte buffer and unsafe. So byte buffer is limited because it's indexed. So it's limited to 2 to 31. So that's kind of small. It's like 2 gigs. And then, whereas the unsafe is virtually unlimited. I say unlimited because it's unlikely that you will run out of that kind of a memory, at least in the forthcoming 25 years. Byte buffer has range checking, unsafe doesn't. Byte buffer provides zero out guaranteed, unsafe doesn't. And byte buffer is kind of harder to free because you have to invoke something called a cleaner, and that's kind of different between different Java versions. Also, there's a caveat with byte buffer. Its hash code and equal actually looks at the entire contents of the byte buffer. So if you, for example, want to put a byte buffer in a map, it's going to be very slow. So you have to wrap your byte buffer into another object. Unsafe, on the other hand, unsafe is unsafe to get because it's varying what kind of Java version you have. Unsafe is unsafe to use because there are no checking of addressing. Unsafe is also unsafe not to use. For example, if you get to call free, you have a memory leak. That memory will never be regained again in your JVM. You have to exit your JVM in order to get that memory back. Unsafe, least and not all unsafe future is unsafe. So I guess they picked a good name. So this is kind of pure geek territory. So stay away from that if you don't have to go there. When we look at read performance, for example, we see that if you allocate on heap, we get a fair amount of performance. It's better off heap, and unsafe obviously has the best performance because you have no safety nets. So this is a very funny example called hello unsafe. Unsafe, put byte at address 0, put something there, and you will get a segmentation fault. Hello unsafe. So it's very easy to shoot yourself in the foot. Okay, so consider using byte buffer over unsafe. The other way is how do you communicate between those 2 memory domains? That's usually taken care of by using something called a serializer. In this case, the serializer takes a certain type, and it has 2 methods. Serialize, which takes an object and writes it into a byte buffer, and as a side effect, increase the byte buffer's position. And there's a corresponding deserialize, which can reconstruct the object from byte buffer from a certain given position. Now, this is a very simplified version of a serializer, but it's only for you now to understand what's going on. So with this, we can go about and create a point serializer that implements support for serialization for our previously immutable point. So it's very easy. If you want to store its content, we just take the X and Y and lay it out in memory. And when we deserialize, we extract some int values, and we create a new point. Looks easy. Okay, so now I'm going to talk about Speedment, which is an enterprise or free version. This will generate everything for you. So let me just play this video. Oops, I didn't have a net here. So that's good that you have a backup slide. So what it does is that it connects to a database, and it retrieves all the metadata from the database. And you have this tool where you can kind of inspect all the tables you have, and then you press the button Generate up on the top of the screen here, and it will generate all POJOs, serialization support, and everything you need to create a program that's using off-heap memory. So table data, for example, are extracted from the metadata. A single table consists of several off-heap byte buffers, because if you have terabytes of data, it can't fit into a single byte buffer. And it has serialization support for primitive deserialization. You don't have to deserialize the entire object. You can just deserialize part of it, like the X or Y component, for example. You don't have to deserialize the entire point object. We also have indexes, which kind of speeds up searching. Like I mentioned, instead of a tree map, we have off-heap indices. And they support a number of operations, the usual stuff like less or equal, in, between, and all that stuff. And the cool thing is that it doesn't matter how much data you have. It's still the same speed, basically. And that's a very important property if you want to handle a huge amount of data. You don't want to have this kind of asymptotic behavior when you run into some kind of wall. And, of course, the data store itself is just a collection of all tables and indexes you have. And it's kind of an immutable snapshot of data from the database. So this ensures thread safety and performed code. And you can kind of create new snapshot in the background. So you're running on one snapshot, and you can create another one. And once it's ready, all your streams will run against that snapshot instead of the old one. And you can have as much data as you have RAM in your server, regardless. It doesn't affect the garbage collector because the garbage collector doesn't see what's off heap. And it can fully decompose a stream into an in-JVM memory primitive operation. So the cool thing here is that you can use streams. And the streams are agnostic. If you don't have the data store, they will use the database. But if you have the data store, they will use the in-memory store. So it's exactly the same API. So if we, for example, run this upper stream here, film rating equals speed 13, and count, it will complete in 160 nanoseconds. And how fast is that? Just accessing 64-bit main memory is 100 nanoseconds. So this is really, really quick. Construct the stream, consume it, and return the result. It's faster than 2 memory accesses. Really amazing. So if you run this even with the Grail VM, it's even faster because, as I told you in the first or second point, it has an optimized C2 compiler, which does better optimization. So now we're really under a single memory access and on average for executing that kind of stream. And that's the shocker. Cool. And you can also do like aggregations of heap. You don't only have to have data there. You can do compute stuff there. So what if you have a group consisting of maybe 1 trillion different groups and you want to create a hash map with that? It's going to consume your entire heap. So you can also do aggregations of heap. I won't go into the details here, but there is an aggregator builder that you can use and work with all your data off heap. Cool. So now we're at the last point. And now I'm going to take a chance. This is the first time I'm doing this. Actually, point 5 was something else when I did this presentation the other times. So I'm going to show you some live coding here. So here I have my project, which is an old project, as you can see there. But the things I'm going to show now is new. So I start a JShell here. And I'm in Java 11. So cool. So I can see now what's known here into my JShell environment. I have a lot of default imports that being set up for me in JShell. So I can add some extra imports like this. And now I have added stuff that's been generated for me by Speedment. So let's check what that is. I have some more, and I also have some standard Java, like collectors, stuff like that. More of a convenience thing. So now I can start and create an application. So now I build my SQL application here. This is just a convenience static method, and I've started Speedment. And let me, before I go into the details here, I usually do this demo with my SQL instance hosted in Oracle Cloud, and then I have Speedment, and then I have my J shell. So this is kind of the setup I have for this demo. Okay, so I have my app here. I can have a new variable called films, and I get it like this. I have a class token here, which allows me to retrieve the film manager, and so I have films, which is a representation of all the films in my remote database. So I can create a stream over them, and I can kind of count them, of course, here, just like this. So I have 1,000 films in my database sitting in Oracle Cloud, and you can see the SQL query that was rendered automatically from my stream. Select star from Sequila film, and it's 1,000 objects. So this entire stream was collapsed to a SQL query, sent to the database, back, and this result was retrieved back in the JVM. So what if I am interested in just the films that was PG-13? So I can, of course, introduce a filter here. So you see now how easy it is to work interactively with this kind of thing. Film, rating equals, PG-13, like that. Cool. So there are 223 films that are rated PG-13. But maybe I'm interested in all the ratings. Maybe I want to kind of do a grouping operation and see what ratings are there in the database. So how can you go about and do that very easily? Because I can use any stream operator that's there. It's really a huge ecosystem with things in streams. So I invoke collect, grouping by, and as a key, I want to group by film rating, and then I want to do counting of all the stuff there, and boom, there it is. So I have a map there with all the ratings from the database. So this just shows that how easy it is to work with streams, with the databases. So let me just close that. So, das, meine Damen und Herren, war alles für mich. Vielen Dank.
So, danke für den schönen Vortrag. Wir haben noch Zeit für Fragen. Wir haben sogar jemanden, der mit dem Mikrofon rumrennt. Hat jemand eine Frage? Bitte Hände hoch und winken. Dort oben einmal eine Frage am Gang.
Hello.
Hello.
How does the SQL mapping handle more complex functions if you map the elements of a stream to something that's just be done in Java and not easily in SQL?
Yeah, so there, of course, there is something called a type mapper that you can apply. So like if you have something in the database, but you would like to view it as something else. For example, you might have a club that you want to be used as a string, for example. There are some mappings you can apply, and you can also write your own mappings and inject them into the tool. Thank you. I just want, more questions?
More questions? Noch mehr Fragen?
There is a question.
Please keep your hand up.
Hi. I was really impressed by the numbers you talked about execution time, but don't you kind of infiltrate what Java is about using direct memory?
Well, I agree in part of your question, because this is more like the C way of coding. So you allocate a bunch of memory and you manage by yourself. Actually, we have our own memory management for off-heap memory. But I don't necessarily think that's bad, because it's advanced under the hood, but in the API it's very easy. You just use stream. So you don't care about the implementation. I think that's a good thing. So you can render it to in-memory traversion, or you can render it to SQL, or you can render it to something else. So I think it's a good complement to Java. Now we can use Java for ultra-low latency, a deterministic response time, and isn't that a great thing? I would also like to point out that since I'm from Sweden, people in Sweden are very shy, so I kind of have some prepared questions, if there aren't any more questions. Okay, that's good. You're not like Swedes, you ask questions, that's good. Yeah, another one. Oh, way back. You have to run.
Do you know the GPA specification APA?
Yeah.
It's not very fun to use, is it?
Well, it depends on your requirements. I think that JPA certainly has its advantages.
Yeah, I use APA on a daily basis, and it's not an improvement to using SQL directly, but sometimes you have to. And now the question, with this filter, does it feel naturally when you have really complex queries with lots of tables joined around, or does it feel like a burden?
Well, it depends, I would say. This is not the solution that will solve all the world's problem. So it has its pros and it has its cons. And sometimes if you would like to explicitly define your SQL queries, you have to use another tool. That's my answer. But I think this covers maybe 95% of the use cases. But there are no silver bullets.
Okay, more questions? We have a few minutes left. Not so shy, the Germans.
No,
here.
that's good. I like that.
Hi.
Hi.
How does Speedman fit into tools like MyBaddies or JOOQ?
Yeah, it's kind of a complementary technology. So you can use them together with other technologies if you want. You're not forced to use only one tool. But of course, they're kind of competing in the same area. And again, it depends on what kind of problem you're trying to use, which one is best for you. This is one tool, and it's good at some things, and there are other tools that are good at other things.
And more questions? So there's one more question.
Is that only for SQL, or can you also use that for MongoDB, for example?
Yeah, good question. Actually, you can use it for anything that can be converted into a stream. So you can use it for like files, like Avro files, or you can. There was even a guy who wrote a Google Doc plugin, so you can stream things from Google Doc. But then you have to write that kind of interface yourself. So out of the box, it supports the most common databases, but you can certainly write a driver for MongoDB or something else.
Okay, next question. Or do we have everybody covered? Okay, looks like. So, thank you very much.
Thank you so much for having me. Okay, take care. Bye.
Thank you, bye-bye. But now I moved back, because I was telling you